Now I'm going to define elementary functions, not the definition. Okay. I'm going to define what we mean by elementary functions. Copy down the definition. I will tell you the meaning using some particular questions. So, okay. An elementary function is a function that can be obtained by a series of operations. Including the operations I mentioned earlier include addition, subtraction, multiplication, division, and more importantly, composition. Okay, including addition, subtraction, multiplication, division, and then more importantly, composition. Actually, it's a very, very huge class of functions. Okay, we need in the course. Now, for instance, I will give you a few. Okay, probably I can write something on this page. Okay, now for example, a power function. So now let's say x squared is a power function. Okay, and we add a power function and exponential function. So now let's say e to the power of x. This one is a elementary function. Okay, it's elementary so because this function can be obtained by adding two building blocks. Okay, two basic elementary functions. I will show you what we mean by composition. Now, for instance, if you have a function y as a function of u is equal to, so now let's say sine of u, and u as a function of x. Now I'm talking about composition. It's super important to identify the composition so later on we will learn how to differentiate the function. You will know how to use the formulas. Okay, so now let's say if y is a function of u as sine of u, you treat y and u as two variables. Okay, and also if u is a function of so now let's say x as u equals, so now let's say x squared, so maybe x cubed. Okay, now look at the mouse cursor. Y as a function of u is sine of u, so which is in the building blocks, right? A sine function, a trig function, which is in the building blocks. And the u is a function of x as x cubed. That's a power function of x. U is a power function of x. Okay. Now listen to me carefully. By performing the composition operation, we mean you kind of plug u equals x cubed into this function, into y equals sine of u. I think you learned composition in high school. Okay, it's kind of a plug-in. Okay. Another example, if y as a function of u is sine of u, if u is a function of x as x cubed, and then after performing the composition operation, then we can treat y as a function of x. It's kind of you plug u equals x cubed into sine of u. Okay, and then we have, so now let's say y as a function of x, y as a function of x. Now look at the mouse cursor. Wherever you see u in here, you replace u with x cubed. So y as a function of x is going to be sine of u. U is now is replaced with x cubed. Okay, we say y is equal to sine of x cubed. The last function is called the composite of two functions. The last function is called the composite of the two functions, sine of u and u equals x cubed. Okay, I will write down the term. Okay, the function here is called the composite. That's the composite of the two functions. So now let's say y equals sine of u and u equals x cubed. Now be careful of the terms. The operation is called the composition, and the resulting function is called the composite. I'm trying to say the operation is called the composition, and that function, the resulting function, is called the composite. Okay, it's comparable to number multiplication. Now let's say if you want to compute 2 times 3, 2 times 3 is equal to 6, right? In this particular case, the operation, the underlined operation, however you write it across or dot, it doesn't matter for number multiplication. The operation now here is multiplication. The answer is the product. You know the term, right? The operation is the multiplication, and the answer is a product. It's comparable to here. The operation is called the composition. The answer is called the composite. So does that make sense? The same thing as for addition. So now let's talk about the term for addition. Okay. So now let's say 2 plus 3 equals 5. The operation here is called addition operation. The answer is called the sum, right? You know that. Okay. Actually, for all the operations you can perform on functions. Okay. You know addition, you know subtraction, you know multiplication, you know division. I just want to make some comments on composition. Okay. After, I'm trying to say, by performing these operations, we can build very complicated functions. Actually, in the future, you just remember if a function can be written using one formula, then the function is an elementary function. Okay. On next slide, on the next slide, I'm going to give you a very complicated one. Okay. You do not even have to copy. In the future, you just remember, as long as you can write a function using one formula, then the function is elementary. Okay. You do not have to copy. Okay. I will give you a very big one. Okay. So now let's say if you have a function something like this. So now let's say natural log. You know the meaning of this notation, right? ln is natural log. So now let's say after that I'll do maybe a quotient. So now let's say square root of. So now let's say sine of. So now let's say I'll try to make a very complicated one. Okay. Sine of. So now let's say tan of. Now let's say x cubed. And then on denominator I will make something like. So now let's say e to the power of tan of. So now let's say e to the power of x. Complicated enough? No matter how complicated, I hope you can see this function can be built from the building blocks by performing something like composition. You said inside you have a composition, right? Taking radical, you have a composition. And on denominator e to the power of something, exponent, you have a composition. And the whole thing is a division. And after taking natural log, you have a composition, right? Again, the bottom line, you just remember, as long as a function can be written using one formula, one single formula, okay, then in most cases, I do not want to say it's true in general. In most cases, the function is elementary. Okay. Now, for instance, a function like that is pretty complicated, but that's a function we are going to study in this course. Now, for instance, we are going to learn how to differentiate a function like that, and also we are going to learn how to integrate a function like that in calculus 2 actually. And by the way, calculus 1 is mostly about differentiation, okay, and the calculus 2 is mostly about integration. So this semester we are also offering calculus 2, in which we are doing integration. We learn many integration techniques, but calculus 1 is mostly about differentiation, the derivatives and so on, okay, applications and so on. Okay, I showed you the meaning of elementary functions. Now get your handout. Now handout 1, please. Okay. We'll keep on go over this list. I think you know how to do part 2 already. Part 2 was on your last assignment, right? Part 4. Now look at part 4. On part 4, you're going to do many questions. A few questions actually. A few questions, like the questions in part 4. I think I told you last time, for the last 2 trig functions, I mean secant and cosecant, I only want you to be able to evaluate the function. Okay. We do not need the graph of these 2 functions in most cases. Okay. And then we move on to part 5. Now look at part 5. In part 5, my intention is to show you some elementary functions. Okay. In question 1, you see the function is built by multiplying 2 elementary functions. One function is exponential function e to the power of x. Okay. You look at the screen. You look at the mouse cursor. The other function is essentially a radical function. Okay. For all these functions, I'm not looking for the graph. I'm not asking you to evaluate the function. I'm only looking for the domain of the function. Okay. Okay. So how about we'll go over the list in part 5. Okay. We'll go over all the functions in part 5. If you can recall what you learned in high school, I think you did a lot of questions about how to get the domain of a function. Actually, in this course, we also need that. Okay, we also need to be able to get the domain of the function for many purposes. Okay. We'll go over the list. Now look at question 1. Okay. So question 1 is simple. Okay. At this point, you need to recall when e to the power of x is defined and when square root of x is defined. And then we are looking for the domain of the function. By that, we mean it's possible to evaluate the function at what numbers? I believe you can recall e to the power of x is defined at any real number. It's possible to compute e to the power of any real number. Okay. And so when multiplying 2 functions, the only thing you need to think about is the square root. Anybody want to tell me the domain of the first function? I'm not going to copy the function here. Okay. If you see square root, wherever you see square root, the x value cannot be negative. Okay. Using the interval notation. Now for question 1, the domain is all the non-negative numbers. I mean square root, right? You need to use the square root to denote the endpoint is included. Okay, now let me try again. So the thing is a little messy. I don't like that. Okay. Again, in question 1, so because you see a square root, x cannot take any negative numbers. So the domain of the function is the set of all the non-negative numbers. Using the interval notation, you have the domain from 0 to infinity. This is the interval notation representing the set of all the non-negative numbers. 0 is included. Okay. This one is simple, right? Now look at question 2. Question 2 is very similar, actually. The cos function is defined at any number. I'm talking about question 2. You look at the mouse cursor. Okay. You remember the graph of cos we mentioned the last time. Cos function is defined at any real number. So the only thing you need to think is when square root of x is defined. So we just mentioned square root. Whenever you see a square root, x value cannot be negative. Okay. So the domain for question 2 is also the set consisting of all the real numbers, all the non-negative real numbers. Using the interval notation, you have that. Okay. Actually, from question 1 and question 2, the only point I was trying to make is that whenever you see a square root or any even radical, so now let's say the 4th root, the 6th root, then x value under the square root, anything under the radical cannot be negative. Okay. Now you look at question 3. You look at question 3. Okay. Now the numerator exponential function with the base of 2 is 2 to the power of x. I'm talking about the numerator of the function. Okay. The numerator is defined at any x value. Exponential function is defined at any real number. If you check your notes. Okay. Actually, you have something on denominator. Okay. Now, can you recall what you learned in high school, or junior high school, or even from the elementary school? Anything on denominator cannot be 0. By that we mean the function is undefined. Listen to me carefully. So question 3, the function is undefined, is not defined only at x values when the denominator is equal to 0. Okay. Okay, I will show you the complete solution to question number 3. In question number 3, the function, I do not even call it the function. Okay. The function is undefined only when the denominator is equal to 0. Now you call it the denominator. Okay, the denominator is x squared minus 4 is equal to 0. Again, whenever you see the quotient of two things, the quotient of two things, the denominator cannot be 0. This will determine the domain of the function. So that makes sense? The function is undefined only when the denominator is equal to 0. Okay, at this point you need to solve the equation for x. So do not only guess. On the left hand side, essentially you have a quadratic function, right? For the quadratic function, to solve an equation like that, actually the proper term is a quadratic equation. To solve a quadratic equation, you move everything to the left hand side and then you factor the left hand side. Okay. To factor the left hand side, I know for some of you guys it's probably a long time since you have done this, but there's a formula I want you to memorize. Okay, the formula is going to be used over and over again. You have a famous formula for factoring a squared minus b squared, right? It's a minus b times a plus b. If you knew that, it's good. If you do not know that, if you do not know that, you need to review something from high school. Okay? I'll try to do my best to review those kind of things you learned in high school. Okay, factor the left-hand side. You have x squared minus 4. You treat 4 as 2 squared. So the equation I just wrote is equivalent to x minus 2 and then times x, yeah, plus 2 or minus 2, that's right. X minus 2 and then times x plus 2, so equals 0. Okay, I'm trying to talk about the general thing. The general thing is when solving a quadratic equation, you move everything to the left hand side, making the right hand side 0, and then you factor the left hand side. Okay, you learn many techniques for factoring a quadratic function, right? So the equation, the solution to the equation, we say the solution to the equation. Okay, the solution to the equation. So in this particular case, you say x is 2 or x equals minus 2. Okay. Actually, I do not want to talk too much about the difference between and or. You just write a comma. Okay. Actually, it's a pretty long story about the logic so between and or. Okay, at this point, you see for question 3, the function is only undefined. The function is only undefined at two numbers, x value of 2, x value of negative 2. Okay. It's kind of, now for question 3, you want to, it's useful to draw a number line in order to write the domain using the interval notation. Okay. On number line, you have the origin. Actually, you do not need the origin, but I always want people to write the origin. Okay. On this side, you have a negative 2. On this side, you have a positive 2. Right. The function is undefined at these two numbers. Now look at the mouse cursor. The function is undefined at negative 2. The function is undefined at 2. Okay. Recall the notation you learned in high school. You draw a circle to indicate the function is undefined at these two numbers. Probably you learned that. Okay. You draw two circles to indicate the function in question 3 is undefined at these two numbers. The number at these 2 points. The points representing the two numbers negative 2 and 2. Okay. And then the function is defined at any other number. Using the number line, we are ready to write the domain of the function. The domain of the function for question number 3. Now the domain of the function for question number 3. These two numbers will divide the number line into 3 subintervals. So that makes sense? To the left of negative 2, in between negative 2 and positive 2, and to the right of positive 2. Okay. You just write the union of 2 intervals. I hope it makes sense. Again, the function is only undefined at 2 numbers, negative 2 and 2. You do not include 0. Okay. To the left of negative 2, you use the interval notation from negative infinity to negative 2 to represent to the left of negative 2, not including negative 2, right? Do not include negative 2. The function is undefined at negative 2. Okay. Union the middle part, the open interval from negative 2 to 2, right? The function is only undefined at these two numbers. The function is defined at any number in between negative 2 and 2, right? That's why you use open interval. I think you got the idea already. And then the last one, to the right of 2, the portion to the right of 2, using the interval notation, you say from 2 to infinity, right? That's how you write the domain of the function. So we are done question number 3. Okay. Now let's move forward to question number 4. So essentially, this part of the review. If I'm running too fast, probably I'm running a little bit too slow for many of you guys. If I'm running too fast, so let me know. I can repeat things. So just don't be shy. So let me know wherever you cannot follow me. Okay. Now you look at 4. 4, you see two things. You see a radical. You see a square root, right? You see something on denominator. Now for question 4, you need to take care of two things. Anything under the radical cannot be negative. Anything under the square root cannot be negative. anything on denominator cannot be 0. You have to take care of two things. Okay. Right. How about we'll also start from where the function is undefined. Okay. Where the function is undefined. Now for question 4, the function in question 4, I'm not going to copy the function. Okay. It's undefined. It's undefined when you check two things. You check two things. The thing is the stuff under the radical, the stuff inside the radical. I think people say it in two ways, either under the radical or inside the radical. The same thing. Okay. Anything under the radical cannot be negative, so which means x plus 1 is greater than or equal to 0. So that makes sense. And also you need to take care of one other thing. You need to take care of the denominator. The denominator cannot be 0. Okay. So we have two conditions. The two conditions, they have to be all satisfied. So both satisfied, I mean. Okay. In order the function is defined. So the function is undefined when the stuff under the radical is not negative, and x squared plus minus 6x is not equal to 0. It's not equal to 0. Okay. Sorry, there's something wrong with wording. Okay. The function is defined, so can I replace undefined with defined? Otherwise, yeah. So this time I want to look at what x values the function is defined. The function is defined when the stuff under the radical is not negative, and the denominator is not equal to 0. Okay. Again, when you see two things, one thing is a radical, a square root. The other thing is something on denominator. You need to take care of the two things. Okay. So we have a system of inequalities. I said inequalities. Inequalities. You have two inequalities. Okay. Now we need to solve the inequalities for x. Okay. The system of inequalities, I read the two things together so because the two things, they have to be both true in order the function is defined. Okay. Eventually we solve the inequality for x. Okay. Now look at the top one. The top one is equivalent to the inequality. You add two sides of the inequality by -1, the same thing as you subtract two sides of the inequality by 1. Okay. The top inequality is the same thing as x is greater than or equal to -1. You see it? You add two sides of the inequality by a number, then the inequality is equivalent. You subtract two sides of the inequality by -1, you have that. You want the range for x anyway, right? We're solving the inequality. For the second one, the left-hand side is a quadratic. Okay. We'll do the same thing again. We factor the left-hand side. For the left-hand side, you have x times x minus 6 is not equal to 0. Right? I did nothing but for the second inequality, I did nothing but factor the left-hand side. Okay. Okay. Now I'm going to make the meaning a little bit clearer. So in the next set, the first inequality, I can do nothing about that. X is greater than or equal to -1. Okay. The second inequality, you look at the mouse cursor. Okay. For the left-hand side of the second inequality, you have the product of two numbers. The product of two numbers is not equal to 0. The product of two numbers is not equal to 0. Then you have two factors. from this, I hope it's not too hard to understand. If you have a product which is not 0, then none of the two factors cannot be 0. Okay. The first factor is not equal to 0. It means x is not equal to 0. The second factor, the underlined factor, the second factor is not equal to 0. It means x is not equal to 6. So that makes sense? In general, if you have a product a times b is not equal to 0, then none of these two factors cannot be 0. If you see the other way around, if one of the two factors is 0, then the product has to be 0. Okay. I think it's not too hard to understand. Okay. At this point, we can use a number line to help to get the domain. You draw a number line again. It's comparable to question number 3. Okay. From the number line, so this time you label a point. You label a point with 0, so that's the origin. Okay. You need -1 in here. You need -1 in here, and you also need a 6 in here. I believe, right? You need a 6. Now you look at the mouse cursor. Okay. For the portion when x is greater than or equal to -1, on the number line, you indicate the solution to the inequality using something like this. I did a dot in here to mean this number -1 is included in the domain. Okay. 0 is not included. You look at the mouse cursor. 6 is not included. From the number line, the same as before, you use a circle to indicate. It's good enough for a circle. You use a circle to indicate this point is not included, and likewise you use a circle in here. I think that's a better circle. You use a circle there to indicate 6 is not included. Okay. Okay. Now we are ready to get the domain. We are ready to get the domain of the function. Okay. You look at the number line. You look at the number line. To the right of -1, not including 0, and not including 6. Now we can use the number line to get the domain of the function. Okay. The domain of the function has a few parts. One part is -1 is included. Okay. The interval from -1 to 0, union 0 is not included. Okay. Now look at the mouse cursor. 0 is not included. The next portion is from 0 to 6. 6 is not included either, right? And then everything to the right of 6 is included in the domain, from 6 to infinity. Okay. That's how to use the interval notation to get the domain. Okay. Any questions about this? So question number 4 is a little bit complicated, but I hope it's not too hard to follow. You solve a system of inequalities, and then after getting everything in terms of x, in the last form, everything is in terms of x, right? X is greater than or equal to -1. X is not equal to 0, x is not equal to 6. After getting everything in terms of x, you are ready to represent the domain with the help of a number line. That's question number 4. If you don't have any questions, we'll move on. Okay. Actually, part 6, I want to skip part 6 for now. My intention for question 1 is ask you to do a complete square, and then with the help of complete square, we can do some curve sketching. But at this point, I want to skip it. I will review whenever you need this. Okay. I want to move on to the next class of functions, part 7. In part 7, you have the form of the functions probably you have never seen before. These functions are called piecewise defined functions. We are going to use these functions to understand some concepts. These functions are kind of important too. Okay. I think I have two guests in this class. If you are in this class, so please try to use your real name. I think I have two guests in this class. Probably it's somebody in this class who doesn't want to show your name. It doesn't matter, so don't be shy. Show your name, please. Okay, now part 7. Okay. Again, in part 7, we want to introduce some new concept called piecewise defined functions. The first thing I want you to know is that these functions, the piecewise defined functions, are not elementary. Okay. We'll use the first question to show you the meaning. Okay. Piecewise defined functions. Now look at the requirement of the function. Okay. To understand the function, we are trying to answer 4 questions: how to evaluate the function, right? How to get the domain of the function, how to get the graph of the function, and also how to get the range of the function. So don't worry too much about question E yet. Okay. We'll only answer 4 questions. Now concentrate. So this thing is probably new to many of you guys. A function like this is called a piecewise defined function. I'm going to write the name. Okay. Piecewise defined function. I will show you the meaning. Actually, the function has 2 pieces. So in this particular case, the function has 2 pieces. I will show you the meaning of actually, still, as long as you are able to answer the 4 questions, then you should be able to understand the meaning. Okay, we'll go over the questions one by one. Probably for the evaluation, I'm going to ask you to evaluate a few more values than these 3. Okay. Probably at this point, I still want to recall the meaning of the function. Now let's recall the definition of the function, the informal way I define the function. A function is treated as a machine, right? Having the condition that there's only one condition for the machine. Every qualified input has one and only one output. So that's the only condition it has to satisfy. Still, you treat the function as a machine. A machine can process inputs and get outputs. Okay. The only condition is that every input has one and only one output. Okay. Now using that, we are going to get the output for some inputs. Okay. Now we'll evaluate the function at 0 first. So this time you watch 2 things. Now look at the mouse cursor. You watch the input. You watch the definition of the function. Actually, the machine has a switch. You can imagine the machine has a switch. By that we mean for x value, it has 2 cases. Okay. I told you to watch the input. So this time the input is 0. Okay. We are trying to get the output for the input of 0. After you see the input 0, and then you check, is the input in this piece, on this piece, or the input is on the other piece? One piece is the condition that x is less than 1. The other piece is the piece x is greater than or equal to 1. The whole thing is still one rule. The whole thing is still one machine. Okay, 0 is less than 1, right? You check the condition. Is 0 less than 1 or greater than or equal to 1? So in this particular case, 0 is less than 1. So the machine will process the input using that formula, using that rule. Okay. Anybody want to tell me the output for the input of 0? I mean the value of f of 0, please. 0 is on the top piece, so you use the formula 2x so to get the input. The answer is right. The answer is coming from 2 times 0, right? To see, so the answer is on the screen is right. Okay, but I'm going to write one more step to show you which formula you are using to get output. Okay, 0 is less than 1. It's on the top piece, so you use that formula to get the output. The output is computed using 2 times the input, 2 times the input of 0. That's why you have the answer of 0, right? Okay, now let's try to get some other values. Okay, some other values. So now let's say the value of the function at 1. Now let's do 1. Okay, we'll do the list first. We'll follow the list first. Okay. You see the input is 1. Now the problem is the input on the top piece or the bottom piece. The input 1 is not less than 1. 1 is greater than or equal to 1, right? 1 is on the bottom piece. 1 is on the bottom piece, so you have to use that formula to compute the output. So that makes sense? Anybody want to tell me the value of 1, please? The value of the function at 1? Yeah, so 1 is right. 1 is right. Okay, I think you got the idea. 1 is on the bottom piece, so you need to use the formula, the input squared. X squared is the input squared, right? To get the value of the function. The value of the function is 1. Okay. I cannot ask you to compute too many values, too many interesting values. I mean, actually 1 is the only interesting value. Okay, now let's get a few more. Okay, the value of the function at 2, please. So anybody want to tell me very quickly? The value of the function at 2, please. 4. 4 is right. You compute 2 squared. 2 is on the bottom piece, right? So you have to use the input squared to get the output. So the value of the function at 2 is 4. So maybe one more. As long as you can do one more, then most likely you got the idea. Okay. Now let's do one more. The value of the function at -1, please. The value of the function at -1. Yeah, -2. Again, I want to repeat this. How we get -2? Okay. -1 is on top piece. -1 is a number less than 1, right? When you see the input is on the top piece, you use the top formula to get the output for the function. Still, okay, I will make more comments soon. So the answer is -2. -2 is computed using the top formula. Okay. Again, I really do not want you to see the whole thing as 2 functions. It's still one function. It's still one function having 2 pieces. You can imagine the machine. It's a machine having a switch, right? The switch is handled by less than 1 or greater than or equal to 1. Any input is either less than 1 or greater than or equal to 1, right? You use the condition to check, and then it will tell the machine how to process the input. So does that make sense? Again, a piecewise defined function is still one function. Do not treat the whole thing as 2 functions. Okay. We answered question 1. Okay. We know how to evaluate the function already. So that's the most important thing. The most important thing is how to evaluate the function, how to get the outputs for the input. Okay. After knowing for what x values you can evaluate the function, Now we are ready to talk about the what I'm trying to say, to talk about the domain of the function. The second question, right? Anybody want to tell me the domain of the function? To get the domain of the function, you think for what x values we can evaluate the function. 0 is in the domain, 1 is in the domain, 2 is in the domain, -1 is in the domain. We are trying to say, is it possible to evaluate the function at any number less than 1? Yeah, -infinity to infinity. That's right. Okay. It's possible to evaluate the function at any real number. Any real number is either less than 1 or greater than or equal to 1. You're given a number, you're given an input, you only have two cases. So that makes sense? For each case, you can process the input. The machine, the function can process the input to get the output. So the domain is the set of all the real numbers. You can say all the real numbers, but you write using the interval notation from -infinity to infinity. That's right. Okay. And then piecewise defined function. So this time the graph is kind of weird. You probably haven't seen it before. Okay. Also, you can plot some points. Now let's recall something I told you before. Each value of the function will determine a point on the graph. Right? The function is defined at all the real numbers, so you have many inputs. Many inputs will determine many points on the graph. Many points will form a curve, but this time the curve is kind of weird. Okay, the curve is the graph of the function. I'm trying to say it's possible to get the graph of the function by plotting some points. Okay. But it's also easier if you know the graph of the function x squared. I think we have seen it. I told you to memorize before. So the whole x squared is a parabola, but for this particular function, it's only part of the parabola. So do not include the whole parabola. I want to repeat. I have seen people doing that over and over again. So do not include the whole. I will make comments later after we get the graph. It's easier for me to comment. Okay, we'll try to do a sketch. Sorry, my coordinate system is not straight anyway. Okay, illustration only. Okay, illustration only. I think I have the graph somewhere, but I was kind of rushed before class, and I forgot to get you the graph. Illustration only. Okay. I'm going to use the dotted line to draw the whole graph, to draw the entire graph. To the right of 1. To the right of 1, you have part of the parabola. The parabola is the function x squared. I will use the dotted line to draw the part of the parabola which is not on the graph of f of x. Okay, now to the right of 1, you have part of the parabola. To the right of 1, it's going to be solid. The solid part is going to be part of the function. It's going to be part of the graph of the function f of x. So do you know what I mean? That's the portion to the right of 1. I was looking at the bottom portion first. Actually, it's probably you want to look at the top portion first. Actually, it doesn't matter. It doesn't matter. Okay. You know the graph of x, right? Y equals x. It's now follow the mouse cursor. The graph of y equals x is a line something like this. The graph of 2x is a straight line with the slope of 2. Okay. You know the coefficient of x is the slope. But it's only the portion for the portion to the left of 1. Okay. The line is passing through the origin with the slope of 2. Illustration only. Okay. I will start from here. When I sketch, I'm going to use the dotted line to indicate the portions which is not on the graph of f. Okay, just say f. And then starting from 1, it's going to be solid, passing through the origin. Sorry, I know the graph is really ugly, but illustration only. I think you know what I mean. Okay, I want to repeat. Okay, I'm going to make some comments now. So listen to me carefully. Okay. Yeah, probably we still want to talk about the portion to the right of 1 first. Okay, to the 1 is here. To the right of x value of 1, the graph of f, the graph of f of x is part of the problem. And to the left of 1, the graph of the function f is part of the straight line with the equation of y equals 2x. The dotted portion is not included in the graph. Okay, I'm going to. I think I have an eraser on my pen. I will try to remove the portion I don't need. So this is the portion. So this is a portion I don't need on the graph, right? So the graph of the function is something like this. I want to repeat, so do not include the dotted part. If you include the dotted part, it's not going to be the graph of the function anyway. Okay. Now let's imagine you had a dotted part. Then remember the one requirement? The one requirement is one input cannot have two outputs. Or if you can recall, you learned in high school, you have vertical line test. Or any vertical line cannot cut the graph of a function at more than one point. We're not 100% done yet. We still need to deal with one point. I will give you the conclusion first. I'm going to make some comments later. Okay. At this point, I'm going to. Oh my gosh. I forgot to turn back to my pen mode. And now I think it's pen mode. Okay. Now listen to me carefully. Okay. At this point, I'm going to use a circle. I'm going to draw a circle at this. Actually, it's wrong. At this point, I'm going to draw a dot. To draw a solid dot. At this point, I'm going to draw a circle. I will tell you the meaning of these two things: the dot and circle. The dot and circle. Now you look at the definition of the function. Okay. The definition of the function. I'm going to use a dot to indicate the value of the function at 1 is given by the y coordinate of the dot. So do you see the dot has the x coordinate of 1 and the y coordinate of 1? I want to repeat, okay? I want to repeat. I'm going to use a dot in here to indicate the value of the function at this 1 is equal to 1. Is equal to y coordinate of the point. You see the value of the function at 1 is equal to y, right? Likewise, so what's the meaning of that hole? This hole, it means the value of the function at 1 is not given by the y coordinate of the hole. I think the hole has x coordinate of 1 and y coordinate of 2. It means the value of the function at 1 is not equal to 2. It means the value of the function at 1 equals 1. So that makes sense? The solid dot, it means the value of the function at 1 is equal to 1. This hole, it means the value of the function at 1 is not equal to 2. I'm trying to say, on the graph, you have to indicate the value of the function at 1 is what number. You look at the dot, right? You do not look at the hole. You look at the dot to get the output for the input of 1. I hope I made the thing clear. Okay. That's a piecewise defined function. Okay. Any questions about this? So probably I'm going to repeat this over and over again later in the course. Okay. Now part 4, item number 4. In item number 4, we are going to get the range. The range should be simple. After getting the graph of the function, the range should be simple. So anybody want to tell me the range by looking at the graph? The range, you take all the points on the graph into account, okay, and then you get the range. You consider the range for y values. It's negative infinity to infinity, right? Any real numbers in the range. Any questions about this? I went over this one a little bit slower, so because most of you guys have not seen piecewise defined functions before. I know it's hard for some of you guys, probably. Okay, you just remember a piecewise defined function is one function having two pieces. Really do not treat the function as two functions. It's not two functions. Okay. In particular for the graph, I really do not want you to draw something like this. Sorry. For the graph, I really do not want you to draw something like this. Part of the parabola, so part of a straight line. That's not the graph of function, right? For if you draw something like this, one input could have two outputs. Or the vertical line, if you can recall the vertical line test, the vertical line here cuts the graph at 2 points, which means this case is not a function. Do not give me a graph like that. On the assignment, you are going to see a question like this. Okay. That's question 1. Any questions? If you don't have any questions, we'll probably go over one more question before we take a break. So before we are done, handout 1. Okay. Temporarily, I'm going to skip number 3. I'll go back to number 3 when we talk about differentiable or not differentiable for a function. That's where we need it. Okay, now look at this function. Yeah, probably for this one I can go over the solution a little bit quicker. I hope you don't mind. I hope you got this. This function is kind of weird, so can I modify the question a little bit? That's probably not my intention. My intention is going to be the following. So forget about this. I'm going to rewrite the function. Okay. The value of the function is 5 when x is, if x is less than 4. Okay. The function is square root of x when x is greater than or equal to 4. Now let's do that. Probably that's not my intention either. But, okay, so we'll redo the question anyway. Okay. The first thing we do is to evaluate the function at some numbers. So forget about the list. I will give you a new list. Okay. Anybody want to tell me the value of the function at 0? Maybe at 0, please. The value of the function at 0. 0 is on the top piece, right? On the top piece, you kind of have a constant function, 5. 5 is right. On the top piece, you have a constant function. It means for any input, as long as the input is a number less than 0, then the value is a constant of 5. Okay, so the value of the function is a constant of 5. Okay, and also, so maybe now let's get one more. The value of the function at 1. The value of the function at 1, please. The value of the function at 1. 1 is on the top piece too, right? That's 5, right? Whenever you see the input is a number less than less than 4, the output is 5. Okay. Now let's get the value of the function at 4. That's the most interesting point actually. Okay. The value of the function at 4, if x is greater than or equal to 4. 4 is on the bottom piece, so you have to use square root of 4 to get the output. Okay. So which is 2. Okay, now let's get one more. The value of the function at 100. At 100, please. The value of the function at 100. You don't need a calculator. I know some of you guys are pressing buttons. It's 10. It's square root of 100. You know, you are looking for a number having the condition the number squared is equal to 100. Thus, the meaning of the square root is 10, right? Okay, so we know how to evaluate the function already. Actually, as long as I give you an input, any input, you can get me the output. I'm trying to say the domain of the function is the set of all the real numbers, right? Any number, you can evaluate the function at any real number. Okay, in this case, I think that's question 2. I will show you the sketch. And by the way, for piecewise defined functions, it's hard for me to use a software graphing calculator, so like Decimal, to draw piecewise defined functions. It's possible, but it's taking a long time. Illustration only. Okay. Now let's say 4 is here. To the left of 4, you have a constant of 5. So now let's say you have 5 in here. Okay. We'll figure out the dot and the hole, so very shortly later. Okay. And then to the right of 4, you have part of the graph of square root of x, the circle. Okay. You want to recall how to get the graph of? I told you to memorize the graph of some power functions before. It's kind of the whole thing is kind of something like that, right? I will still use the dot. Okay. I think the value of the function at 4 is equal to, it's kind of the solid part is going from here. Now I'm going to remove the dotted part. I still don't know how to use this. I will draw the whole thing again. Now let's say 2 is here. Okay, I'm looking for the answer to the following question. Now try to answer my question. Okay. There should be a dot. There should be a hole. So just tell me, is the dot on top or at the bottom? Is the dot at the solid circle, the dot on the top or at the bottom? At the bottom. Okay. The value of the function at 4 is equal to 2. So you see when x is greater than or equal to 4. Or you can see the value of the function at 4 is 2. So this point has to be on the graph, right? This point is on the graph, and correspondingly there's a hole in here. Yeah, that's right. I think all of you guys got the right answer. Again, that's a hole. That's a dot. You look at the mouse cursor. Okay. So maybe it's not too clear on the graph, but that's what I meant. Now let's get the range for this one. Okay. Anybody can see the range? So just look at the graph. Anybody can see the range? This point, the solid dot has x coordinate of 4 and y coordinate of 2. It's actually the value. It's actually determined by the value of the function at 4. Anybody want to tell me the range? The range, please. 2 is in the range, right? Anything greater than 2 is in the range. So 2 is included, yeah, from 2 to infinity, that's right.